Welcome back, curious minds. In our previous video, we explored the electric field created by a single point charge. But what happens if we have not just one but a bunch of them? In fact, most of the charges we encounter in the real world aren't simple point-like substance. You can derive the answer to this question from Coulomb's law. This is a further fundamental fact about the world that we live in and can know only from doing experiments by making observations which we have been done over many years. In today's video, we are diving deep into something called the superposition principle and how it generalizes our previous knowledge for extended charged objects. So let's get started. Through a series of incredibly precise experiments, scientists have found that electric forces follow a rule known as the superposition principle. But what exactly does that mean? Imagine a system that takes in a single input and produces an output in response. Now, if we input A and get output X, and input B and get output Y, what happens when we combine those inputs? When we add input A and input B together, then output X and Y add up as well. That is, input A plus B produces response X plus Y. This is referred to as principle of superposition. Systems that are driven by this principle are known as linear systems. Many physical systems out there can actually be modeled as linear systems. So having a solid grasp of the superposition principle is absolutely vital. Now, in the context of electrostatics, we can state superposition principle like this. The electric field created by 2 point charges at some point is the vector sum of the individual contributions from each charge. Let's break it down. Imagine if only charge Q1 was present. It would create its own electric field. Let's call it E1. Similarly, if only charge Q2 was present, it would generate its own electric field E2. But when both charges are present simultaneously, the total electric field at point P, let's call it E, is obtained by summing up E1 and E2. That is E is equals to E1 plus E2. Now this may sound obvious to you, but it doesn't have to be this way. In fact, there are fundamental laws of nature which don't work like this at all. Like the forces between quarks doesn't follow the superposition principle. Imagine we have a whole bunch of point charges, n of them to be exact. Now if we want to know the electric field at a specific point P, we need to apply the superposition principle repeatedly. That is, net field at P is equals to E1 plus E2 plus E3 and so on. Or in more compact form, E is equals to summation of EI, where I varies from 1 to n. Here EI is the field generated by the charge Qi when all other charges are removed. Let's say R1, R2, R3 and so on be the position vectors of the charges Q1, Q2, Q3 and so on respectively. Then field at point P having the position vector R will be given by this expression. So far, we have considered a collection of discrete point charges, but really we need to generalize our equation for some continuous distribution of charge, because very often the charged objects that we are talking about have charge distributed throughout their volume with some density. So we need to learn how to handle the possibility of some blob of charge. Suppose we have a blob of charge here and we want to determine the electric field at this point P created by the entire blob. Okay, the idea is first I will break my blob up into lots of little cells. In each of these cells, there's a little bit of charge. Now we can treat each cell as a point charge and apply Coulomb's law to calculate the electric field at point P created by each individual cell. Let's pick this cell and say it contains charge del Q1. According to Coulomb's law, field at P created by this cell is del E1 is equals to 1 over 4 pi epsilon naught del Q1 by R1 squared times R1 hat. Similarly, for other cells, we get del E2, del E3, and so on. According to the superposition principle, to obtain the total field, we have to vector add up all of these electric fields from each cell. That is, electric field at P approximately equals to del E1 plus del E2 plus del E3 and so on. However, this equation only provides an approximation since our chosen cells are still not point-like objects, rather have a definite volume. To get the actual field, we need to increase the number of cells indefinitely, or in other words, make the cell size arbitrarily small. And this will turn our summation into a definite integral over the source. Here dq is a generic differential charge element. This is our final equation to determine electric field for any distribution of charges. In the upcoming videos, we will calculate electric field for some specific continuous charge distributions. The charge densities that we are going to look at will be simpler in their geometry. Okay, that's all for now. I hope you have enjoyed this deep dive into the electric fields. If you did, don't forget to like and share with others. Click the link in the description to download my notes on this topic. Be absolutely sure to hit the subscribe button for more awe-inspiring scientific adventures. Until next time, keep exploring, stay curious.